So one thing that's kind of bizarre is actually that final theorem we did about the ex post incentive compatibility of that auction. I actually don't know who to credit that to. I haven't seen that precise statement actually stated anywhere. So I'm sort of drawing from 4 different papers from the 80s. I mean, I'll post them on the course site if you want to have a look. But anyways, yeah. So sort of drawing from what seems like a circle of ideas, more than any one particular source. Okay. So time to move on to scenario number 4, which happily, by and large, will be easier than the unit demand setting we just did. There's one non-trivial complexity which shows up, which is the main reason I want to spend some time on scenario 4. Plus, it'll be a cool auction. That's another good reason. And then again, looking ahead, so so what we're starting out with this class, the first 3 weeks or so, is I basically want to focus on the tractable special cases where we can get everything we want. Everything I want, I mean, we get a really strong incentive guarantee. So for ascending auctions, it's this epic guarantee. We get total surplus maximization, and we get it using auctions which are computationally tractable. Okay, so there'll be lots of situations where it's simply impossible to get all of those things. And what I'm doing in these first few weeks is trying to give you a really thorough grounding with when we can get all of it. And so next week will be the culmination of that, and it'll be this very fundamental class of preferences called substitutes. And the way I'm sort of structuring this is I want to make it so that in some sense will be the convex whole of everything we've seen so far. Okay, so we're looking at all these different scenarios that on the one hand, are fundamental in their own right. Like the theory of unit demand bidders, I think, is very nice and very rich. But on the other hand, I think it'll be much easier to understand these so-called substitute preferences with all these special cases to kind of fall back on. Okay, so that's kind of the bigger picture. All right, so scenario 4. So we're looking at multi-unit auctions, meaning we're going to go back to the identical goods case. So scenario 1, you might recall, was identical goods and unit demand. So now we're going to generalize the unit demand assumption, and it's going to be what's called downward sloping valuations. So we have M identical goods, but people in general want more than one, okay? And so the way we're going to model this is Vij is going to be your marginal value of getting a jth copy of the good, given that you already have j minus 1. Okay? And so these, as usual, will be known only to the bidders. So the private marginal value of jth units. Okay? So if I give you some amount x of goods, then I sum up these Vij's for all j of most x to get your overall value for all x of the goods. Okay? All right, so this is clearly not unit demand, right? So unit demand would be the special case where these are 0 whenever j is 2 or more. Okay, that would be unit demand. Right, but downward sloping, we will assume that Vi is non-increasing. Okay, and as you'll see, we're going to use this assumption over and over again. Okay, it's actually quite, this problem gets a lot harder without this assumption. We may or may not talk about it later in the quarter. Okay. Good. So our goal is the usual one. We want an ascending auction with all the good properties. Okay, so epic and surplus maximizing and so on. And as usual, it might be a good idea to start with a sanity check and just ask, well, at least can we have a DSIC direct revelation version? And again, because it's surplus maximization, we sort of know what we should be doing. We should be doing the VCG mechanism. And I know you all know what this is, but there's a reason I'm doing this. So in the VCG mechanism, right, you just ask people for their private valuation. And then the allocation rule is you're just like, okay, let's take the bids at face value and maximize surplus. Okay? And so the thing I want to focus on right now is I want to understand that, for scenario number 4, surplus maximization is actually a pretty understandable problem. Okay? It's not that hard to do. In particular, it's polynomial time, but even beyond that, it has some nice structure. So think about this for a second. Okay, so the allocation rule of the VCG mechanism is max surplus with respect to the BIJs. So obviously you could enumerate over all feasible allocations and just pick the best one, but there's definitely a better way to, a smarter way to do this. Right? So like what kind of algorithm is sufficient for this? Just a greedy algorithm. Okay. So basically you take all the BIJs for all I and all j, you just sort them from high to low, and you just take the top m of them, the highest m. Okay. So with two bidders, that may, maybe you're giving 7 to one of them and 3 to the other. Maybe they're interleaved. Maybe B1 of 1 was the biggest, B1 of 2 was the second biggest, and B2 of 1 was the next biggest, and so on, but whatever. Okay? So greedy is good enough. So that's what I want you to notice at the moment. And then you have your usual VCG payments, charge externalities. And we're again going to be shooting for an ascending implementation that simulates the VCG outcome. So it's again going to be essential that we have a sort of better, more structured understanding of what these payments are. Okay, to have any hope of having them, fall out of some ascending implementation, we need some understanding better than just that abstract one. Okay, and we'll do that. Do that when we get there. But at least the fact that the allocation rule is so simple, indeed, this is even simpler than in scenario number 3. Right? Unit demand, it was polynomial time, but it was matching. Right? Matching is not a trivial problem. This is kind of a trivial problem. Okay? So that bodes well. So why spend any time on the scenario at all? Well, there is sort of a new challenge here, which is our approach from the unit demand setting through Walrasian equilibria is not going to work for scenario 4. Okay? So VCG outcome need not be Walrasian equilibria. Now, Walrasian equilibria I only defined for unit demand bidders, but it's quite straightforward to extend the definition to say this situation. So again, you would just say unsold goods have price 0. And now you'd say instead of everybody getting their favorite good, everybody would get their favorite quantity at the current prices. Okay, so there's some 4 goods and they each have some price, and then I have some value for 4 goods and I'd subtract the sum of the prices on the 4 goods. And it should be of any quantities that I could possibly have. With respect to the current prices, I get my favorite quantity. So that would be a Walrasian equilibrium. Okay, again, prices and then an allocation. And so the claim is that here, the VCG outcome need not be one of these Walrasian equilibria. Okay? It's sort of interesting because if you think about it, in the unit demand case, actually we proved a whole bunch of things, all of which were a priori non-trivial. First, for these unit demand bidders in scenario 3, we showed that there exists a Walrasian equilibrium, which again, a priori is not obvious at all. And for more general preferences, you'll even lose existence. Okay, so first there exists one. Second, there exists a smallest one that's component-wise smaller than any other Walrasian equilibria. Third, the VCG payments were always at most any Walrasian equilibrium. But then fourth, you actually have equality at the smallest one between the VCG payment and Walrasian equilibria. For this setting, you still have those first 3 properties. There still exist Walrasian equilibria, there's still a smallest one, and all of them still upper bound VCG payments. We just lose the 4th. We lose equality. It could be the VCG payments are strictly less than every Walrasian equilibria. I'll show you an example. All I need are 2 bidders and 2 goods. So suppose we have 1 bidder with an additive valuation. Okay, just gets 2 units of value for each good that it gets. And then we have 1 unit demand bidder. Okay, who only wants 1 good and is willing to pay 1 for 1 good. Okay. So the VCG outcome. So how do you maximize surplus? Well, clearly you should just give both goods to bidder 1. What does it pay? It pays the externality. So it takes the surplus that it rips away from other people by virtue of it being there. If it wasn't there, then bidder 2 would get its good for a value of 1. It doesn't get anything with bidder 1 there, so the externality is 1. So that's its payment. Bidder 1 gets 2 units, and the total payment equals 1. Because remember, VCG doesn't really assign a price to each good per se. It assigns a payment to each bidder. With unit demand, it was natural to induce, it gave you induced payment price on goods, which is just what did the winner of it pay. But so in this context, it's just the total payment of the bidder one is 2. Okay, is 1 for the 2 goods. Now, could this arise as a Walrasian equilibrium? And again, Walrasian equilibria, you actually have, by definition, you put the prices on the goods. Okay. Well, so to simulate the VCG outcome at Walrasian equilibrium, bidder 1 has to pay 1 total. Okay, so the sum of the prices on the 2 items is going to be 1. Okay. So it could only correspond to a Walrasian equilibrium. Price Q with total price 1, which means one of the prices is less than 1. Okay, because they sum to 1. They're both non-negative. But to be at a Walrasian equilibrium, and for bidder 2 to get nothing, it has to be happy getting nothing. Okay, but if there's some good out there with a price less than 1, then this bidder's like, dude, I would have totally paid that for that good. I would have paid 1 for it. Okay, so bidder 2 is going to be unhappy if the sum of the prices is exactly 1. Okay, so that's the sense in which you cannot realize a VCG outcome in general with a Walrasian equilibrium. The prices are just too low. Okay. All right. And so on the exercises, I'll ask you to think more about Walrasian equilibria in this scenario, because again, a lot of the nice properties still hold, just not this coincidence between the VCG payments and the smallest of the Walrasian equilibria. So, how can we go forward? How can we pursue the possibility of an ascending auction in scenario 4? So we can't get VCG outcome and smallest Walrasian equilibria because they're not the same. So we have to pick. Okay? So either we could try to shoot for an epic auction with a non-VCG, but Walrasian equilibrium, maybe smallest Walrasian equilibrium outcome. Or we could give up on the Walrasian equilibrium property and just try to get VCG. Okay? But we have to do one of these. One would be challenging. Okay, so at some future point, I'm still trying to figure out when. So later, we'll show that 1 is impossible. Okay. So one thing which I'll put on the exercise set is just kind of a very special case of this, which is if you just try to implement, even just say like a direct revelation mechanism. So suppose you just ask people for their valuations, there is a smallest Walrasian equilibrium, just charge them that. Okay, so the first thing that we're going to just note is that that's not DSIC. Okay, so if you don't use the VCG payments, but instead you use the Walrasian equilibrium payments, it doesn't work. Okay, those of you who maybe remember something we talked about in passing last quarter, we talked about something called demand reduction. And that's kind of the problem with trying to use these Walrasian equilibrium prices. The problem is that a bidder might have an incentive to get fewer goods, but much cheaper. Okay? And so the VCG prices are lower precisely to take away the incentive for that kind of demand reduction. Okay? Now that just shows that one particular approach doesn't work. Really what's going on here is that if you want to be surplus maximizing, so we talked about this in single parameter mechanisms last quarter, where if you fix the allocation rule, it pins down the payment rule up to a constant. And there is an analog of that for the problems we're talking about here. And at some point, I'll figure out a time to say more about it. Okay? So, but again, the high level bit here is that if we want a surplus maximizing auction, it's just not going to work for incentives to simulate any other payment rule. Okay? So we just have to punt on Walrasian equilibria. It's just not going to work. So that's what I'm going to do next. So coming up next, we're going to do this. Okay? All right. Good. And so I mean, frankly, the whole approach, the whole order of operations in accomplishing this is going to be exactly the same it was in scenario 3. Happily, kind of every single step is considerably easier. Okay? But so the first step is we're going to say, well, you know, we already mentioned this, but so if we're shooting for these VCG prices, let's have a better, simpler understanding of what they actually are. Okay, we're not going to have an ascending auction that just goes to these very abstract externality charging payments. So what's important is, so we understand what the allocation rule looks like over here in this scenario 4. Let's understand what the payments look like. So VCG payments revisited. Okay. All right. So what do I mean by charge externalities? So again, what does this mean? This means max possible surplus for others. Okay, so you imagine deleting I and now just optimizing purely for the other n-1 people. So obviously in a multi-unit auction, that would mean you just look at all ways to allocate these m goods where bidder I gets 0 of them. All m are given to the other n-1 people. And then you subtract the surplus of the others in the VCG outcome. Okay, so in other words, you look at the surplus of the other n-1 people if you optimize purely for them, minus their share of the surplus when you optimize for all n people. Okay, so again, this is the completely general definition. So now let's think about what that looks like for multi-unit auctions. Okay, and we're going to use the fact that surplus maximization is a greedy algorithm. Okay, and again, this should feel even better than scenario 3. Scenario 3, we had these two matching problems. Now we just have these, each of these is just the outcome of some greedy algorithm. Okay, where I'm running the greedy algorithm here I'm running it on a subset of the bids as here. Okay, with I's, all of the Bij's deleted when I run this algorithm. Okay, so what is this? What is this expression in blue? So fix I. And let's say it gets xi units in the VCG outcome. All right. And so what I want to do here is I want to look at other bidders, BKJs, in sorted order. Okay, from high to low. And this is exactly the relevant input for this computation. Right, so for the max surplus, deleting I, what would I do? I would sort all the BKJs for k not equal to I, and then I would just take the top m. Okay. Now, the relevant regions, so from high to low here. So first we have amongst all of these other BKJs, and again, remember, by downward sloping, these are just sort of, right, so each person's, again, think about the truthful bids. Right, each valuation is already sorted high to low. So this is just some interleaved version, right, of different people's sorted valuations. So over here, of all of these, we have the highest m minus xi. Again, xi is how many bidder I gets. Okay, so maybe there's 100 units overall. This guy got 10. So these are the top 90. Okay. Then we have the next region, which are the next xi highest. And then we have everybody else. Okay. These are the rest. So these top guys, which of these two computations do they participate in? Which of those two allocations? Both, right? So when I is there, it still only gets 10. So 90 go to other people, and of the other, who do they go to? They go to the highest BKJs. Okay, so these are in both. These xi guys, or 10 guys, these are really important, right? These are precisely the BKJs that get allocated after I delete I from the optimization problem. Okay, so these are 10 units that were not allocated to these other n-1 bidders. I delete I, and now suddenly they are. So the sum of the BKJs of these xi units is exactly the increase in surplus to the other n-1 people. Okay? So in other words, the difference between those blue quantities is exactly the sum of the BKJs in this region here. Okay? Okay, so only after deleting I. All right, and then these really are irrelevant. We could imagine even just deleting these from the input if we wanted. Okay. Okay, so good. So that sounds simple, and it is. All right, but so let's actually articulate this structure in a way that'll be useful for us, in a way that, you know, we could imagine maybe computing with an ascending auction. Okay, so what we're doing now is we're having the analog of reformulating this as smallest laws in equilibrium. We're going to reformulate it as something actually even simpler. Okay, so equivalent. All right, yeah. So okay, so bidder I gets some xi units, like 10 units, and the overall payment of bidder I is exactly the same sum of these xi things. Okay, like 10 things. So it's going to be convenient to kind of ascribe. Even though VCG just gives sort of an overall price that bidder I has to pay, it's useful to kind of, you know, think of that as there being a price for each of the xi goods that it gets. Okay, so it gets xi goods. We're going to think of these xi BKJs as supplying those xi prices for the different goods. Okay, and notice those are different prices. Okay, these in general will be different numbers. Okay. So specifically, let's think about. Let me actually define. So this is for some good that I actually gets in VCG. So we can write this as this is a little bit of a mouthful, but so what I'm going to do is for the first good that bidder I gets, I'm going to charge it the lowest of these xi. Okay, so the first good is its highest value, and that is the good that's going to be given the lowest price. Okay, and so then for each successive good that it gets, its marginal value will be going down and down and down, and the pricing going to be attributed to it will be going up and up and up. Okay, so m minus j plus 1th highest BKL, where here k is somebody other than I. Okay, so for example, when j equals 1, that just says for the first good that bidder I was granted, I'm going to think of charging the lowest of these xi bids to it. For the second good, that's the price. For the third good, that's the price. For the fourth good, that's the price, and so on. These are sorted high to low, so these prices are going up. Okay, so that's all this says here. Okay. And so the one way we can understand the VCG payments is just for a bidder I that's granted j goods, it's paying this, or it's paying this formula for each of the units that it gets. So some things to note, we've already talked about this. So first of all, right, just by definition. So what I'm trying to point out is there's some kind of, you know, in effect, we're taking some kind of supply and demand curves and crossing them. That's basically what's going on in this mechanism, okay? So just by assumption, by downward sloping, we have this property. So the value for each incremental unit is going down and down and down. By the way, I've defined these VCG prices. They're going up. So at the end, and so therefore for all of them, it's going to be the case that VI of xi is at least PI of xi. Okay? So the price I'm charging for the highest, and therefore for all of the units, is at most the smallest value, and hence all of the values of all the units you got. So why is that true? Well, we just need to check the last one. So the price for the last guy is just going to be this BKJ. And when I is actually in the computation, right, all of the xi's that are allocated intersperse with this top region. Okay, that's because they were allocated. Right? So these are people who lose when I is in the picture. Okay, so all of these BKJs are lower than the top xi of the ones that belong to I. For the same reason, if I go one more in this sequence, the inequality flips. Okay? So VI xi plus 1 is at most, again, I can define this equally well for any j, so let me actually do that. Okay, for exactly the same reason. Okay, so for the xi plus 1 bid of bidder I, that was actually not allocated by the VCG mechanism, which means it didn't make it in the top M. By contrast, if I plug in xi plus 1 here, all of a sudden I'm talking about this bid, okay, which is part of the top M. Okay, so this was in part of the top M, and this was not, so this is smaller. Okay? And so again, the way to think about this is just, there's basically some values, marginal values, by the bidder, and then in effect, implicit in the VCG mechanism is some sort of price schedule, right? So it's like, oh, you want, well, for the first good, it'll cost you this. Oh, you want another? That'll cost you this. Another? Okay, that'll cost you this. With some increasing price schedule. And what the VCG mechanism is implicitly doing, it's for each bidder looking where they cross, and it's giving the bidder I exactly the units, so that for the region where the values are at least the prices. Okay? And again, one thing to notice, as you'd sort of expect, so these VCG prices, this is totally independent, as you'd expect in a DSIC mechanism, independent of I's reports. Okay? So one way to think about it is just the other n-1 bidders bid. They bid whatever they bid. As a function only of their n-1 bids, so all of their BKJs, that fixes the PIJs. Okay? So you can think, there's actually sort of a Wazian equilibrium interpretation here, although the prices are bidder specific. Okay? So in Wazian equilibrium, we had these just single set of prices, one for each good, and every bidder walks up, faces the same prices, picks their favorite. Here, and this is sort of a general statement about DSIC mechanisms, if just for a bidder I, okay, as a function of what the other bidders bid, now all of a sudden it's again like you're walking into a supermarket. Okay? Or it's really here, it's like sort of a Pez dispenser of goods, if you're old enough to know what a Pez dispenser is. Right, and so we're basically, each good that comes out of the Pez dispenser has a price tag, and each one is higher than before. And the obvious thing to do is just, keep taking them until your marginal value for the next one decreases the price tag on the next item coming out of the Pez dispenser. Okay, and so what this is saying is, in effect, what the VCG mechanism does for you, it looks at the other bids, it sets up these price tags, and then it optimizes on your behalf. It gives you exactly the optimal quantity at that price schedule, given your values. Okay, okay. Good. One more thing I want to say about the VCG prices. Right, so, okay, so why am I not happy? Okay, so this is progress. I think intuitively, this seems, very well structured, very sensible. It's still, right, so again, remember, we're trying to simulate these in an ascending auction, ultimately. We don't know what it's going to look like yet, but we want to compute these. And this is still looking much more like something in a direct revelation mechanism, right? I'm really referencing all of the bids of all the other people, right? So I'd have that in a direct revelation implementation, but the point of an ascending implementation is kind of to, obviously you do learn people's bids or values in the iterative auction, like in the English auction, the original one. You learn when people drop out, so you can back out what their valuations were if they're playing truthfully. But you sort of learn them on a need-to-know basis. Okay, and this doesn't have that flavor, this expression. This kind of references all of the bids. So I want to do one more step and sort of reformulate this yet again, so it has more of this flavor of something you could learn on a need-to-know basis. All right, and it's very, it's kind of immediate, no hard work here. So also equivalent. So now I want to define it in terms of demand queries. So again, ultimately we're going to have some auction where we're going to have some price, we're going to ask people what they want. So I want some version of PIJ that references people's demands. So let me tell you, so what is a demand in the context of scenario 4? Well, it's just going to be, at a given price per item, what's your optimal quantity, okay? So let's just say the maximum number of goods J, so that VI of J is greater than Q, okay? So if I tell you that you have to pay Q dollars per unit, okay, for this to make sense, it has to be downward sloping, okay? I've used that over and over again, right? So, your value per unit's only going down, so to know how many units you want before you should stop, you just go until the marginal value drops below the price per unit, and that's the right amount. Okay? So D at Q is just how many you want at a given price Q. Okay, so now, here's another way to write pi of j, okay? So let's just take j equal 1 for starters. So j equal 1 is the mth thing here, okay? So it's just the value of whatever's in this box. Okay, so there's some number here. So here's how I'm going to define it, okay? So imagine actually so what does this demand say? This demand says, for a given bidder, how many values do you have above this price? And so the thing I want to notice is, what's special about this threshold is if I just go slightly above this threshold, that's exactly where everybody else's demands is exactly, the sum of them is exactly m minus 1. Okay, so say the 100th, say the mth BKJ here is 173. Okay? Now consider the price 173 plus epsilon. There's exactly 99 BKJs out there belonging to the bidders other than I that are bigger than 173 plus epsilon. Okay? So I can characterize the m minus j plus 1th highest number in here as the infimum of all the thresholds, so that the sum of the demands, i.e. the sum of the VKJs above this threshold, is exactly m minus j. Okay? So if you don't see this in real time, it's just stare at it later. Okay, there's nothing. Yeah.
This reminds me of the Clinching auction.
That's exactly what we're doing. That's exactly what we're doing. There was. Excellent. Very good. That's right. So this may be familiar to some of you. This was on a problem set in 364A. Absolutely. So yeah, I figured that was 3 months ago, so thought you might be a little rusty. But
no, if you had to write it out in LaTeX.
Awesome. 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 Okay. You're excused for the rest of the lecture if you want. It sounds like you've earned it. Okay, so good. So Pij is, where'd it go? Yeah, inf. So the smallest price at which everybody else's demands drops. A lot of the stuff I talk about, you might want to just think about the case where all of the VIJs are distinct, where there's no ties. A lot of this simplifies. I'm going to do it in the general case, but that might be easier to just parse real time. So I'm going to write inequality here. It's the first time this drops to below m minus j. But if there are no ties, then there's going to be this is going to be equal. It's going to be the same thing. Okay. Again, the point is just imagine kind of sweeping a threshold from right to left. And you're asking, okay, what is the point at which there's exactly m minus l people to the left of me? And that's going to be at the m minus l plus 1th highest bid. So why did I do this? Well, so here's a characterization of the VCG price, which is referencing only the demands of people. Okay, so all I need to know are what are the quantities people want at some sequence of prices, and that actually tells me exactly what the price should be. So that's starting to feel like exactly something that would unveil itself over the course of an ascending auction. Okay, and that's what we're going to do. Okay. Good. So as advertised, let me tell you about the Clinching auction. So last quarter we did, so what I'm going to tell you now is the original Clinching auction by Azubel. So last quarter I told you about an extension of the, so we're doing it historically out of order. So last quarter we talked about a variant that was motivated about problems with budgets, which is not what we're talking about now. So now we're just in the usual quasi-linear model. So one reason people have been building on this mechanism is because it extends to budgets more easily than other ones. But this quarter we're more focusing on the ascending auction aspects. Okay, so this is the original one just for welfare maximization with no budgets. But what's nice about it is it gives an ascending implementation in scenario 4. Okay. Good. All right. So this again will just be one of these auctions where we start the price at 0 and we raise it and we wait. And so basically we have the invariant that demand is bigger than supply. And as soon as the demand drops to be supply or less, we stop. So we try to equalize supply and demand. Now, on the other hand, remember, we definitely don't want to terminate with the laws in equilibrium. We want to terminate with these VCG payments. And these VCG payments charge different things for different goods. Okay, or at least the way we're thinking about them. So we want our ascending auction to have that property also. Okay, which like the English auction did not have that property. The English auction, you had this current price, and all the winners paid that same price at termination. So we don't want that. We somehow want the prices to change over the course of the auction. Okay, so we're going to sell stuff along the way, not merely at the end. The stuff we sell earlier will be at lower prices. Okay. All right, so initialize. So P equals 0. So there's this case I'm going to ignore, which is that even at 0 price, the demand is at most M. Okay, so in that case, just give the goods away for free, and you're fine. So suppose at least at price equals 0, there's sort of over demand. Okay, so ask bidders. So at each iteration, at the current price, we ask bidders how many they would want at this price. And again, remember, that's just very simple. Really just asking, look, how big a prefix of your VIJs exceed P? Okay? So as P goes up, there's going to be, of course, fewer and fewer VIJs that are bigger than P. Okay? So these demands are going to be, assuming bidders bid honestly, these DIs are certainly going to be dropping over the course of the auction. So ask bidders for their DIPs. Those are the queries we're going to ask them. So if, again, the demand has dropped, halt, and I'll tell you in a second about the allocations and payments. All right, but the main loop is as simple as could be. Okay, you just keep increasing P by epsilon until the demand drops to be at most of the supply. Okay, and that's going to happen eventually, obviously. Okay, so allocation. Now, in the simple case, and you might want to go ahead and think about this, the simple case would be, you have some iteration where the sum of these is exactly M plus 1, say, and then you bump up P by epsilon, and then it drops to exactly M. Okay? And so that's an easy case. So if the supply equaled the demand, you would just give people the demanded quantities in that last iteration. Now, in general, especially when you've discretized like this, for all we know, the total demand is going to drop from M plus 1 to M minus 1. It'll just skip M. Okay? And basically, we're just going to, we're going to always allocate all M of the units, and we're just going to basically do it arbitrarily amongst those sort of demands right at the threshold. Okay, so formally, so the final allocation, the Xi's, each bidder I will get at, so they'll get at least as many units as they demanded in the final iteration. And they'll get at most as many units as they demanded in the penultimate iteration. Okay, so the sum of these is bigger than M by assumption. The sum of these is at most M. Okay? So give them that. So units to each I subject to allocating all items. Okay? And it's not going to matter how you do this. Okay? These are the only constraints that matter. Okay? But again, in the simple case, you might want to think about that the sum of these just equals M. And then there's a unique choice of what to do there. So let's talk about the payments. And, really, for the payments, we're basically just going to copy this formula, okay, up to the epsilon. Okay. So with this understanding of VCG payment, so if you haven't done this work of sort of trying to understand the VCG payments in terms of demand queries, it's hard to see where this comes from. But given this groundwork that we've laid, hopefully these payments will seem very sensible. So for the jth good, that a bidder I gets, I guess I suppose bidder I gets J or more goods. And for the jth good, we're going to insist that it pays, okay, so there's going to be a minus epsilon, but the main point is that you do the earliest, meaning the lowest, price Q, so that the demand of the rest of the bidders So these are over the prices Q that were actually tested by the auction, right? So what do we have here? Here we have an infimum, right? So in effect, the auction has just discretized that into multiples of epsilon. Those are the only things we actually sort of queried people's demands at. And we're just saying, well, what's our best approximation of this infimum? Let's just look at the lowest price at which this condition held, okay? At which that was at most, the first price, the first price at which that was at most m minus j. Okay. Let me actually write this to be more symmetric with that. Min Q okay, where again this refers to the prices at which this auction actually queried bidders. Okay. And this Q must exist because at the end of the auction, if nothing else, the highest price we ever tried, the sum of all of the demands was at most m. Okay, so at that point, because bidder I got at least j items, the sum of everyone else's demands has to be at most m minus j. Okay, so if nothing else, the price at the last iteration will satisfy this. Okay, so that's the clinching auction. Right, and this has all the properties we want. Okay, so we have to prove those things, but again, the proof is definitely easier than scenario 3. Okay, but that's the whole auction. Let me just make sure this makes sense. Let's just go ahead and run it in the example, which had no Walrasian equilibria. So remember, we had a additive bidder, value 2 for both. We had a unit demand bidder. Okay, so let's try to understand what are bidders' demands. So D1 of Q, so what does that look like? So as a function of Q, what's bidder 1's demand?
It's 2 and then drops to 0 when Q hits 2.
Right. Right, so remember, the demand is just how many units would you want at that price, i.e., how long a prefix of your valuation, of your marginal valuations exceed Q. Right, so bidder 1 is just 2 comma 2. So as long as Q is less than 2, both of them do. If 2 is at least 2, none of them do. Okay. So D1 of Q. And then similarly, D2 of Q is 1 for Q in 0, 1. And 0 thereafter. Agreed? Okay, so then looking at the clinching auction, and let's assume that 1 over epsilon is an integer. Then basically what's going to happen is even in the very first iteration, right? So even in the very first iteration, the demand, so think about it from bidder 1's perspective, right? The demand by others is only 1, right? So there's 2 units. The demand for others is only 1, even at the beginning, even when the price is 0. Okay? So that basically means that bidder 1 will clinch its first unit at the beginning of the auction at a price of 0. Okay? So in other words, I guess ignore this minus epsilon for right now. But so basically, even at 0, this is going to be true. Okay? For j equal 1. Now, for this to be true for j equal 2, we have to wait until the price goes up to 1, so the demand of the other person drops to 0. Okay? So then the demand of everyone else is at most m minus 2, at most 0. And so that price 1 is what the first bidder will get that second unit at. And if you remember, those are exactly the VCG prices. Right? So bidder 1 was supposed to pay a combined value of 1 for both. That's happening. 0 for the first unit, 1 for the second unit. Okay? All right. So so that's just sort of a toy example of the warm-up, but let's actually prove that this holds in general. And I want to do exactly the same, again, order of operations for unit demand. I want to first just do an analysis under sincere bidding. And I want to show you that, up to epsilons, we in some sense simulate the VCG outcome, specifically the utilities of bidders in the VCG outcome. And then, as we know, that gives us something automatic for these consistent deviations, but we want to prove it works for all deviations. And happily, that's much easier in this case than for the CK option for unit demand bidders. Okay, analysis. And again, for now, we'll just assume without justification sincere bidding. Okay? So first I want to talk about the surplus. Then I'll talk about the bidder utilities. So let's first at least prove that this auction, assuming sincere bidding, gets the allocation right. Again, not worry about the payments. So the claim is that surplus of clinching is within the number of goods times epsilon of the max possible. Okay? So it's pretty easy. So the benchmark is VCG. And so the VCG allocates to the top M BIJs. And the surplus is just the sum of those. Okay? Actually, with sincere bidding, let me just write V's. Okay. So that's where we'd like to be. Now, assuming sincere bidding, what do we do? What does clinching do? Well, the last two iterations of the clinching auction identify two nested sets of bidders. Okay? So basically two nested sets of these VIJs. So in the last iteration, it identifies a set of VIJs all bigger than P. And again, so this is, I can understand if people don't see this, but if you don't see it, it's purely because you don't have the notation mapping solid yet. This is a trivial statement. So let's remember we're thinking about the final iteration of the auction, okay, when it halts. So there's some current price P, $100 or whatever. What is DIP? That's just how many units do you want at $100? And again, that's just sort of what's the length of your prefix. Okay, so for how many J's is your VIJ exceed 100? Okay. So a DIP is just a collection. So if DIP equals to 10, that's just a collection of 10 VIJs that are bigger than that threshold. Okay. So by virtue of halting with the sum of the DIPs at most M, that corresponds to a set of these entries in people's valuations whose size is at most M. Okay. So needless to say, whatever cardinality this is, these are the highest of all of the VIJs. So this is a subset of what gets allocated in VCG. And then in the penultimate iteration, we identify a similar set with a slightly lower threshold with size bigger than M. Okay? So the optimal solution corresponds to a superset of B1 and a strict subset of B2. Okay? And so we allocate to all of B1 and rest to B2. And so the only error we could possibly be making is on VIJs that lie between P and P minus epsilon. Okay, so we're just making this discretization error of up to epsilon. We waste at most epsilon surplus for each of our units, so overall at most an epsilon times M surplus loss. Okay. Any questions about that? So another way to think about it is this is approximately solving the top M, sorting problem. Okay. All right. So at least the allocation's basically right. So in unit demand, we then moved on to say that the prices were basically right. Okay, so here, because it's not unit demand, it's actually a little awkward to try to talk, sort of directly about prices. So instead what I want to do is I want to talk about bidder utilities, which if you think about it, when you reason about deviations, that's what you actually care about. You just want to say bidder's utility is basically the same no matter how it deviates. So as long as we preserve those well, all of the usual arguments will hold. So, okay, so this was the assertion, this is 1, and this is the proof of 1. So here's the assertion 2, that the clinching auction, basically has the same bidder utilities as the VCG outcome. So for all bidders I, utility in the clinching auction, assuming everybody bids sincerely, is equal to the utility in VCG up to plus minus m times epsilon. Okay? And if you think, so this is the analog of saying we got the payments right. Okay? Let me keep that. So let me argue this, proof of 2. Oh yeah, so let me just remind you. So basically the way I'm going to prove this is I'm going to remind you the sense in which we can think about the VCG mechanism as kind of optimally solving this, supply-demand curve, crossover point for a bidder. And then I'll argue that the clinching auction is solving almost exactly the same problem, just with, sort of slightly different prices. So the utility is going to be, basically the same. So let me just remind you what's up with VCG, right? Because that's one thing we're comparing to, right? So imagine we were actually doing VCG and everybody revealed truthfully what their private valuations were. What would things look like from I's perspective? Okay. Well, from I's perspective, before it even submits anything, so just as a function of the bids of the other bidders, the bids of the other bidders define these prices, these PIJs. Okay. So again, there's nothing I can do about this price schedule. Okay, the price tags on the Pez dispenser. Then, as a function of bidder I's valuation, as a function of its value, marginal value for each of the next goods, what the VCG mechanism implicitly does is it just says, well, I'll give you items at the prices until it's not worth it for you anymore. Okay, the prices only go up, your values only go down. At the point that they cross, I stop. So in other words, I can think of the utility in VCG as being the maximum over the number of goods. So basically I just take the differences of your marginal values and the marginal costs, and as soon as these become negative, I stop. So let me write this way. Max, so basically if your marginal value is bigger than the marginal price, then you get it. Otherwise it's just 0. Okay, so this is just saying, truncate this sequence once they cross, and then just sum up in the rest. Okay, so this is the utility of bidder I in the VCG mechanism using this notation. Okay, so in that sense, the VCG mechanism, it defines PIJ independent of the valuation, and then it solves this problem optimally for bidder I. Okay, so now I want to argue the clinching auction is basically doing the same thing. Okay, under sincere bidding. So that's what's up in VCG. In the clinching auction, so in the clinching auction, I forgot the notation here. So this I'm going to define as QIJ. Okay, so PIJ is the thought experiment. Suppose we ran the VCG mechanism with everybody's truthful declarations. The QIJs are suppose we run the clinching auction with everybody bidding sincerely. And this is how they're defined. Okay? Okay. So the first thing to notice, and this is really just by construction. Oh, shoot, I erased the definition of PIJ. Okay. So let me rewrite here what was the reformulation that we had. So this was the infimum over all Q, such that everybody else's demand is at most M minus J. Okay? So the sum smallest Q for which this, the point I'm just trying to make is the Pij's and the Qij's are almost exactly the same by definition, right? This is just the smallest of all real numbers Q, so that this is, at most M minus J. And this just says, oh, well, if we restrict ourselves to multiples of epsilon, what's the smallest Q, so that this is below M minus J? Well, at worst, by discretization, it's an epsilon higher, then I subtracted epsilon from it. So Qij is going to be only less than Pij and by at most epsilon. Okay? So the prices are almost exactly the same. The one thing, so the one, I have to do some more, so why aren't we done? Okay? So remember that, Pij is the price you're going to pay for your jth copy if I give it to you. Okay? Qij is the price you're going to pay for the jth unit if I give it to you. Okay? So if I knew that a bidder I got exactly the same number of units in both, then I'd be done. Because you get the same amount and you're paying exactly the same amount for each, so you'd be done. So I still have to do some more argument because I have to argue that you don't get radically fewer units for some reason in the clinching auction, and therefore your utility sucks. I have to argue that. Okay. So why is that true? So basically I'm going to claim that in the clinching auction we're essentially optimizing this for the bidder. Okay, just with the Q's instead of the P's. So the Q's are almost the same as the P's, the utility is going to be almost the same. So if I is given at least J units in the clinching auction, then, all right, so again, maybe just to back up. So what are we hoping is going to be true? So we know that, again, the Qij's are defined completely independent of what I does. And from I's perspective, what it really wants the clinching auction to do on its behalf, given that it's going to be paying Qij's, it just wants it wants the clinching auction to give it, again, the J units up to the point at which its value would drop below the price Q. Okay, that would be the clinching auction optimizing for bidder I on its behalf. All right? So let's look at two cases. So we're hoping on the one hand that when its value is at least this price Q, it gets it, and on the other hand, when the value is below the price Q, it doesn't get it. Those are the two things bidder I wants. So suppose bidder I does get a jth unit, then the claim is it must be the case that it wants it. Okay? And so why is this true? I mean, this is true sort of by the definition of the clinching auction. So what is the largest number of units you might conceivably get in the clinching auction? Well, the most you might get is the amount that you demanded at the price of the penultimate iteration. Okay, P minus epsilon. And any units you get, what's the biggest price you might be charged? Right, so in other words, you would be totally happy to have this many units at a price of P minus epsilon. Okay, you're not going to get more than these units. And what's the maximum price you could be charged? Well, the most it could be would be that last price, P, and then we also give you an epsilon bonus. Okay, so you're happy with whatever you get. That's not the problem. So the other thing, the claim is that if suppose I does not get at least J units, so ideally we'd be able to say, well, the only reason that can happen is because the price, the Q, is more than its value, the V, and that is true, but up to an epsilon. Okay. So then, if it doesn't get its jth unit, then the only reason could be that its value is at most the price, at least up to an epsilon. Okay? So this is slightly trickier, but not much. I'll talk through it, but that's probably a good thing for you to think through also. So why would this be true? Okay, so suppose, let's see, so why is this true? So suppose you didn't get J. Why would that be true? That would mean in the final iteration of the auction. So notice, again, by construction, whatever you demanded in the very last iteration of the auction, when this demand drops to M or below, you're definitely getting that much. Okay? So if you don't get J units, it means at the last iteration you said you didn't want J units, right, at this price of P. Okay? And so why would that happen? Well, that would basically, I mean, then you just have to sort of substitute the value of the Q's, but I mean, this is the condition you'll get. Okay? So I'll leave it for you to check that. All right, so, and the claim is then we're done. All right? So think about the VCG outcome, what is your utility? Your utility is exactly the outcome of this maximization problem, where you just look at the differences of the V's and the P's, as long as they're positive, and you sum them up. What do these 3 points argue about the clinching auction? It says it's essentially your utility is the result of exactly the same optimization problem. The only difference being instead of the P's, you have the Q's. Those are at most epsilon different, so they matter at most m times epsilon for utility. Plus, if this difference is less than epsilon, you might get 0 instead. Okay, so that's another at most epsilon per unit. Okay. So therefore, utility differs by at most 2 epsilon m. Okay. So this is the analog of in the unit demand setting in scenario 3, where we said that the outcome of the CK auction for every good J, the price was the same as under VCG up to plus minus epsilon times mn. Okay, so this is the analog. The utility of a bidder is essentially the same whether you're talking about the truthful outcome of VCG or the sincere bidding outcome of the clinching auction. All right, so questions about that? We're almost done. All right. So that's enough to say that, so because we're simulating utilities under the VCG mechanism, and because the VCG mechanism is dominant strategy incentive compatible, no deviation can help you, this says that consistent deviations won't help you either under the clinching auction. Because again, there's just this mapping between your utility in the VCG mechanism with a given declaration and your utility in the clinching auction under a given consistent action. Okay, it's just exactly the same. So again, the issue is just what about inconsistent actions? What about crazy actions? Can that ever help, assuming other bidders bid sincerely? Remember, we're always assuming other bidders bid sincerely. We don't know their valuation, but we know they're not being crazy. So theorem, last one for today. Clinching auction is epic. All right. Yeah, so this is actually, I mean, basically the proof of this is already on the board. Okay. So, fix a bidder, fix valuation profiles. Assume other bidders bid sincerely, which is important. I'll leave it to you to think about that. So what we need to show is that a best response up to some function of epsilon by I is optimal. Sincere bidding is optimal. Okay. So here's the main reason it's important that other bidders bid sincerely, right? So in the clinching auction, at the end of the day, right, so eventually the clinching auction is going to terminate, okay? And, you know, whatever I does, it's going to get some stuff. It's going to get J units of stuff, okay? And given that the other bidders bid sincerely, always answer the demand queries correctly at every price they're ever asked, given that they bid sincerely, the price Qij that bidder I is going to have to pay for its jth unit, if it gets a jth unit, it's going to be this number. Okay? There's no action available to bidder I that can change the price it's going to pay for a jth unit if it gets a jth unit. Okay? Now, if the other bidders were not bidding sincerely, if they were like monitoring what I was doing, then all bets are off. Right? So if somehow I's behavior would change how the other bidders would answer the demand queries, forget about it. Okay? But sincere bidding in particular means that the way you answer your demand query doesn't depend on anything that happened in the past. Okay? So these are just going to be whatever they are. And so this price is going to be whatever it is. All right? So if you think about it, like let's actually give bidder I way more power. Okay? Let's actually just say we're going to let you pick however many units of this good you want directly. You just pick J. Pick how much you want. Just the catch, you have to pay QIJ for the jth unit. Okay? But subject to that, do whatever you want. Well, what did we just argue happens in the clinching auction? We just argued that the clinching auction essentially maximizes exactly that optimization problem. Okay? Sum over all j of the max between 0 and v ij minus qij. Okay? So the only thing the clinching auction did wrong in optimizing this optimization problem for the bidder is, well, there might be some units j where this difference is less than epsilon and you don't get it. Okay? So it might cost you m epsilon. Right? That's the only error we make. All right? So the point is, forget about actions. Even just let bidder I pick units directly, but it can't affect the prices. And then bidding sincerely is optimal up to epsilon m. Okay? So, but again, the crux, the whole point is that you can't influence the prices. Given that, there's just nothing you can do. All right? So since I's action can't influence the QIJs, and sincere bidding optimizes sum over j, max 0. Yeah, that's right. Done. Okay. So, any questions? All right. So, again, just sort of zooming back out to the big picture. So for these 2 weeks, our goals have remained totally invariant. Okay, it's always asking when can we get these awesome ascending auctions. We now have 4 scenarios where we can do it. And the point of showing you all these different scenarios is that different scenarios have been hard in different ways. Right? So for example, in the unit demand situation, the whole trick was to use these Laurasian equilibrium equivalents. And we lost that in the multi-unit downward sloping case. But we had other structure which sort of saved us and still allowed us to get our eventual goal. So it's natural to ask, is there some common framework that you can think about both of these as special cases? That's one question. Another question is kind of, is there some, inherent maximal frontier of bidders' valuations, that characterizes when we can have these awesome auctions and when we can't? Okay? And so the answer to both of those questions are yes. And again, the key will be to understand these substitutes valuations, and that's what we'll start next week. So see you then.